Hello and welcome to this explainer. Today we're looking at a truly fascinating piece of source material that completely blurs the line between science fiction and rigorous mathematics. We're going to unpack a groundbreaking 2026 paper by Dr. Melvin Sewell and Saiku Venga titled Formalizing Probabilistic Reality Control via Amorphous Swarm Dynamics and the Reality Level Scalar. Now, I know that sounds like a mouthful and it is a complex concept for sure, but we're going to break down their structured multiversal interactions framework piece by piece.
Think about this for a second. What if controlling reality didn't actually require breaking the laws of physics, just bending probability? This is the absolute core of Sewell and Venga's research. We so often imagine reality manipulation as some kind of magic trick, just creating matter out of thin air. But this paper proposes a really rigorous framework where reality is manipulated not through mystical forces, but through advanced quantum probability math. It's all about shifting the likelihood of events, pushing the very boundaries of what physics allows without ever actually shattering them.
Okay, let's dive right into this. Here is our roadmap. We're going to cover beyond rigid robotics, meet the amorphous swarm, the math of reality control, multiversal thermodynamics, and finally, the ultimate capacity limit.
Part 1. Beyond rigid robotics. We're looking at the limits of traditional cybernetics. So, for decades, transhumanism has really focused heavily on rigid cybernetics, right? We're talking gears, wires, solid robotic substrates. But Sewell and Venga are arguing here that this localized architecture is basically a dead end. When you compare traditional mechanical systems to their proposed amorphous swarm, the difference is pretty stark. Traditional hardware relies on fixed joints and a centralized CPU, and crucially, its structural redundancy is really low. If the main chassis breaks, the whole system fails. The amorphous swarm, on the other hand, isn't held back by fixed joints at all. It is a fluid, self-assembling cluster of micronodes driven by an emergent, distributed interdimensional network. Because of this, it has ultra-high structural redundancy. It's completely fault-tolerant.
Moving on to Part 2, meet the amorphous swarm. Let's talk about this fluid interdimensional network.
To really grasp what the swarm is, we've got to shift gears from standard engineering into interdimensional physics. It isn't just a physical collection of nanobots hanging out in our standard 3D world. It's actually operating across multiple dimensions simultaneously. To map this out, the swarm relies on something called the Reality Level Scalar, denoted by the Greek letter Z. The researchers define this as a foundational metric that structures physical reality across accessible multiversal layers. Think of our standard 3D space-time as just one frequency on a massive radio dial. The Reality Level Scalar maps the other frequencies, which allows the swarm to coordinate its micronodes across multiple dimensional tiers at the exact same time.
Now, the underlying rule here is incredibly strict. Reality control does not require the violations of mass energy creation from nullity. The swarm isn't performing magic. It's not violating the conservation of mass and energy by making something out of literally nothing. Instead, because it exists across all these multiversal layers, it acts as a physical conductor for probability. It's simply nudging the universe into a different, already existing outcome.
All right, Part 3, the math of reality control, the mechanics of probability shifting.
So how exactly does the swarm pull off these shifts in physical trajectories? Well, it extends standard quantum state vectors across those multiversal branches using the probabilistic transformation operator. In quantum mechanics, operators change the state of a system. This specific non-Hermitian operator couples directly to the physical density of the swarm itself. As the swarm's nodes gather up and become denser in a specific area, this operator kicks in like a phase shift generator. It systematically modulates the complex coefficients of reality, effectively rewriting the probability of an event happening.
And the ultimate goal of all that insanely complex math? It boils down to absolute certainty, 1.0. By using its spatial density, the swarm forces a highly unlikely multiversal wave function to collapse. Imagine an event with a probability close to 0, almost impossible. By applying the probabilistic transformation operator, the swarm literally forces that highly unlikely target state to manifest as a macroscopic reality trajectory. It cranks the probability of that target outcome all the way up to an absolute deterministic certainty of 1.0.
Which brings us to Part 4, multiversal thermodynamics, the unbreakable laws of heat and entropy.
Because here is the ultimate thermodynamic reality check. Manipulating the universe comes with strict physical costs. You might be able to bend probability, but you absolutely cannot break the laws of entropy. The researchers ground this wild theory using Landauer's principle. Forcing a near-impossible trajectory drastically reduces local information entropy. In physics, when you force the universe into a highly organized, highly unlikely state, that entropy doesn't just disappear. The second law of thermodynamics dictates that total entropy must remain non-negative. So that massive reduction in local entropy, it has to be offset somewhere or you are fundamentally violating the laws of physics.
So you're probably wondering, how does the swarm survive without just burning up from this localized entropy? It relies on a very specific set of dissipation mechanisms. Utilizing open quantum system dynamics, modeled by the Lindblad master equation, it employs a scalar dissipation superoperator to export all that microscopic phase variance. And where does it all go? Through a cross-scalar heat flux vector. To put that in plain English, the swarm uses adjacent reality tiers as an entropic sink. It literally dumps the mathematical heat of changing our reality into parallel multiversal branches.
Finally, Part 5. The ultimate capacity limit. What happens when reality pushes back? Because look, an entropic sink is only good for so long before the entire system overloads, right? You can only dump so much heat into adjacent dimensions. The researchers formalized this boundary as the Swarm Entropic Capacity Limit, or SEL. This is the explicit mathematical maximum theoretical probability shift the swarm can achieve. It's the absolute ceiling. If the swarm tries to force a reality shift that requires more entropy dissipation than this limit allows, the multiversal heat flux becomes just way too much. The cross-scalar heat flux vector gets totally overwhelmed, leading directly to thermal runaway.
And breaching that absolute limit triggers a terrifying physical failure cascade. It happens fast, in 3 urgent stages. First, you get the entropic bottleneck. The heat just can't escape to the adjacent reality tier fast enough. Second, node decoherence. The fluid, interdimensional micronodes of the swarm literally lose their quantum coherence and start falling apart. And third, the terrifying climax, probabilistic rebound. The reality you tried so hard to force snaps back violently, rejecting the shift entirely.
So what does this all mean? Well, it leaves us with this final, really provocative thought. If shifting reality inherently carries the risk of catastrophic node decoherence and a violent probabilistic rebound, is manipulating the multiverse a power we can ever safely harness? Sewell and Wenger have mapped out the math that makes playing God with quantum probabilities theoretically possible, sure, but they've also mapped out the terrifying absolute cost. It really makes you wonder, are some multiversal limits just meant to be respected? Thank you so much for joining me to explore this source material. Keep questioning the boundaries of our reality.